Let us define the following matrix Mij. Define Mij as the partial derivative of phi I with respect to xj. And we know that when t is equal to 0, this matrix is the identity matrix, because phi becomes x. Then we compute the time derivative, which is partial squared phi I partial t partial x j, and we also compute the time derivative of the inverse matrix, which, as you know, is minus inverse of m time derivative inverse of m. But at t equals 0, both m's are 1, so you have minus m dot at t equals 0, which means that m dot minus 1 ij is equal to minus m dot at t equals 0. Oh yes, yes. What is m dot at t equals 0? This. We can actually exchange partial xj, partial t, and then we know that partial phi partial t goes to a, so that is minus, so for t equals 0, that is minus partial j a I. That is minus partial j a I. So yes, so you have the result, because you see that in this derivation we have indices I and j. Here we have j and I. So you have an exchange of indices. This is minus partial I aj, this is minus partial j ai. And I recall that this is precisely the expression of the commutator of two vectors in local coordinates. You can check it from previous lectures. So that is precisely the Lie derivative. Now we check the Lie derivative of one form, and then we move to the Lie derivative of the metric and its meaning. So let omega denote a one form. Again, we flow it, which means consider omega I of phi t x d phi, or omega I of phi t x partial phi I partial x j dx j. And then the Lie derivative is the partial derivative of this calculated at time equal 0. And what is it? So again, you have to differentiate here. Here you will have omega I. We jump already directly to t equals 0. The, partial j, and then you will have partial phi j partial t at t equals 0, which is a j, times this object, which becomes just the differential. This is a unity for t equals 0. Then you have to differentiate this again. So you have plus omega I of x. When t equals 0, phi becomes x. And then you have this derivative, and that you can exchange. And when t equals 0, partial phi I partial t becomes a I. Okay. So you have aj partial j omega I plus, here we have to change the name of the indices, omega j partial I aj dx I. And you can check that this is exactly so. Let's see. Vi dj then you have the derivative of Vi. You see the index of the derivative is the same as the index of the differential. Let's check, which is okay. The index of the derivative is the same as the index of the differential. So this is again okay with the previous definition. And so on. This is the definition of Lie derivative. Most interesting thing is the Lie derivative of the metric and actually of every object, because every Lie derivative we have just computed determines the infinitesimal transformations under changes of coordinates, diffeomorphisms. So these are infinitesimal diffeomorphisms. Why? So let's take the metric and repeat the same. So here the product dxj, I dxj is symmetric. We do not specify it. So we have to compute the derivative of what? gij phi phi tx, the partial phi I partial xk partial phi j partial xm dxk dxm at t equals 0. Now it's just a repetition of what we did before. So when the derivative acts on gij, you will have something like the derivative along the vector field, al partial L. When the derivative acts on the others, you will have something like this. So plus gij, so partial over partial t of that will be partial kai. And the second, this one, will be a delta jm. And then you will have partial delta I k, and here you see partial m aj. Oh yes, here we had deltas also. So, what do we have? AL partial L gij. Let me collect dxi dxj. Then here you have g, I is saturated, so L partial k partial becomes I, a L, j becomes m, that's okay, j. And the other one, this is ik, so this is k, but k is I, j L partial m, which is j a L. Yes. And this is the Lie derivative of the metric along the vector. Or you can also say in components it is this thing. Why are these the infinitesimal diffeomorphisms? Maybe you have recognized that or not. Let us do it. So when you change coordinates, and the change is infinitesimally close to the starting coordinates, you have this kind of change of coordinates. And then you know that the metric, the transformed metric, G prime mu nu of x prime is G rho sigma of x. And then you have dx rho dx partial x rho partial x sigma partial x prime mu partial x prime nu. And this is also G prime mu nu of x prime, but x prime is x plus the function psi. Then you Taylor expand that to the first order. So you have G mu nu prime of x plus, to the first order, this is psi rho, partial rho, G prime mu nu of x. Then you also know that to the first order, this derivative, you take the derivative, take the derivative of that, delta mu rho plus partial rho psi mu. And then the inverse, partial rho partial x prime, let's say nu, will be what it takes to have 1 when you multiply this. So it will be delta rho nu minus partial rho psi nu. Let's check. No, partial nu psi rho. Because when you multiply this like this, the cross contributions cancel out. So there you can write from this identity, let me move this object to the other side. You can write G mu nu prime of x equals minus psi rho partial rho G mu nu prime of x, but to the first order, this G mu nu prime can be replaced by G mu nu because it's already multiplied by psi, so we do not need that. But then you have to compute that one to the first order. So yes, the first contribution, by the way, is this we can say for last. Let's do first that. So there will be a delta for both that gives G mu nu of x. And then there will be some minuses. You see minus partial mu x rho G rho nu. And then there will be the same with nu and rho exchange. Minus partial nu psi rho G rho mu. Okay. And then you can check that this is precisely the Lie derivative of G mu nu. The difference, a minus if you want, we have a minus. Because the Lie derivative is this combination here. So you have psi partial psi rho partial rho, here it is. And then you have these two other contributions, which are exactly the same. So you do have this. This is how the metric changes in the same point x. Okay, so you compare g prime not in x prime and g in x, but g prime in x and g in x. So you study what is the change of g, not what is the change of x. But that's for every field. So if you have a scalar field, you know that the transformation is this. But that is phi prime of psi plus x, which to the first order is phi prime of x plus psi rho partial rho phi prime phi. And so when you compute the difference phi prime of x minus phi of x, you get to the first order minus psi rho d rho phi, which is the Lie derivative of a function, as we checked earlier. And that's it. So that is what the Lie derivative is about. Lorentzian manifolds. We assume that there exists a metric with, it's assumed, an invertible so it's everywhere invertible metric with signature one minus one minus one minus one. 4 dimensions, or whatever dimensions you want, is assumed. So this, the existence of such an object is assumed. Again, this is a cross-section of the symmetric product of two cotangent bundles. And now we move to the notation we will use in physics. So this matrix will be called eta mu nu. Coordinates will be written like this. Partial derivatives will be shorthanded to this. So we have differentials and derivations, which are dual to each other. So this, now we have to keep track of upper and lower indices. So this is lower and upper index. This you see is an upper index for x, but it is in the denominator, so it becomes a lower index. Then we will have nabla, the nabla partial mu of partial nu, which we know defines the Christoffel symbols, and we will write them like that. Then we had the basis EI such that GEI EJ equals delta IJ. This will go into what the basis will be called E, small e with indices, new type of indices, small a, and since there is a signature, we cannot diagonalize, orthonormalize the metric, but we can define the basis EI so that this holds. So EI are vector fields. It's a basis of vector fields. And we can also convert to the other basis, and we will have coefficients like this. These are functions of x, because a vector is a combination of derivations of the basis times functions of x locally. Then we will have nabla EA on EB will be some coefficients. For the moment we call them gamma ABC EC. So these are the Christoffel symbols in this basis. The indices A, B, C will be called flat space indices. And these, the indices mu, nu, rho, will be called spacetime indices. And yes. So these objects, E, A mu, basically are what takes us from one type of indices to the other type of indices. Notice that the basis EA is defined locally, as well as the basis of derivatives partial mu, that's defined locally. So when you have intersections of charts, you will have to do something, because two charts may have different bases EA. But the transformations of bases EA is quite simple. We will see the details of that. It's not. It's an algebraic transformation. So this, well, little by little, we will understand how these two things work. Now we want to introduce differential forms. To the vectors EA. And we will call them EA, but indices will be raised. So these will be differential forms with certain, in the other bases, they will have this expression with some h, a mu, which are functions of x, and we want them to be dual to the vectors, which means that they have to satisfy this. So let's see what we get. Delta EB equals EA EB. That means let's replace H A mu dx mu and EB instead is what we wrote this way. So EB nu partial nu. Then we just know that this can be taken out. And we remain with this thing, which is delta mu nu. So we have this relation which just tells us that H are the inverse of E. So that means that H A mu is the inverse matrix of A mu A. Notice how I displace the indices just for clarity, but they won't be displaced any longer. This matrix is written like this: E A mu. Same symbol E, but now why there is no risk of confusion, because in one case the space-time index is a superscript, and in this case it is a subscript. So what we have from there is an identity like this, delta AB. And this allows us to define differential forms, which will look like this. E superscript A equal to E A mu dx mu. Now, you know that the inverse of a matrix is unique, and so if you have A, B equal the identity, you also have B, A equal the identity. And that means that we also have first this one. So let me write that identity by displacing the indices for clarity. This is delta A B. If we do B dot A, this, we have E mu A, E A mu equal delta mu mu. So we necessarily have this relation, which we will not write with displaced indices any longer, just like this. Which means that these E matrices with indices placed in this way are inverse of each other, and you can either contract flat space indices and you will get the identity with spacetime indices, or you can contract the spacetime indices and you will get the identity with flat space indices. Then another identity we can use, we have it already, it is this one. G EA EB is eta EB. Let's see what we get from that. G EA EB is eta AB. But what is GEA AB? This is the metric contracted with the vectors. And the vectors EA EB have these components with spacetime indices on top. B. But now we know that we can invert, we have the inverse of this, so we can multiply eta AB, but by something like E, let's say A rho E B sigma. Let's replace E A rho E B sigma, and instead of eta AB we have G mu nu E mu A E nu p. Now we know that these products, here there is you see a contraction of indices A, so this times this is equal to delta mu rho, and the other gives delta bb delta nu sigma, and once you contract by the two deltas, this is g rho sigma. So you have this identity. G mu nu is equal to eta AB EB nu EA mu. And this is how you go from one metric to the other, the metric in space-time indices and the metric in flat space indices, by means of this object, which is called tetrad or Vierbein. For dimensions, you can use Vierbein. And you can use it to convert space-time indices and flat space indices into each other, or to raise and lower indices. So yes, so for example, if we take this and multiply it by E nu C, we get E nu C E mu A eta A B E B nu. Then when we contract these two things, this is delta BC. So you have E A mu eta A C. So that means that you lower or raise flat space indices with eta, and you lower space-time indices with G. Okay, so for today it's enough.